Let's consider a formal example. I have to find the series, Fourier series, either the exponential series or the sine-cosine series of the following function. The function is defined as x if x lies between 0 and 1, and 0 if x lies between 1 and 2, and it's said to be periodic. So what we do is this: we first plot the graph. So between 0 and 1, including 1, I'll have x. So I'm going to include 1. And then from 1 to 2, excluding 1, I'm going to have 0. And then it's periodic, so it keeps repeating like that. And on this side also it's periodic, so it keeps repeating there as well. So this is the periodic function we have, and the value of this function at the highest point is 1. Now clearly this function is piecewise continuous and its value is defined everywhere, so the hypothesis of Fourier theorem holds. So we can find the Fourier series. So what I'll do is, since the exponential series might be new to even those who have seen Fourier series before, I'll focus on the exponential series. So we wish to write f of x as the sum from n equals minus infinity to plus infinity of Cn e to the I n x. Now let's be careful here, because that would be the case if the interval were minus pi to pi. But the interval here is of the form 0 to 2l with l equals 1, or 0 to 2. So what we have to do is we have to use one of the forms suitable for that. In that case, you're going to have e to the I n x pi over L. So since L is equal to 1, it's just going to be, let me just write this anyway. Okay, that's the form you have to use. So L is equal to 1, so this gives me sum from minus infinity to infinity Cn e to the I n pi x. So that's the form in which we need the series to be written. So this part is really important for you to figure out the normalizations before you start. The Cn's themselves can be got by finding the Fourier coefficients. So that can be done by using the formula 1 over 2l. But since it's going from 0 to 2l, I take the integral from 0 to 2l. And I get f of x e to the minus I n pi x over L dx. That's the formula. Oops, not dx down here. That's the formula I'm supposed to use if I have something going from 0 to 2l. Now all we need to now do is substitute the function value f of x and the proper limits and the proper value of L. So this is going to be integral 0 to 2. L is equal to 1, so that's going to be 1/2. Well, from 0 to 2, it's going to be 0 from 1 to 2. So I only have to worry about from 0 to 1. And f of x is x there. So e to the minus I n pi x, L equals 1, so I don't worry about writing that dx. This can be integrated by parts. I'm going to write this as the u function and this as the dv function. Well, off to the side, let's play the integration by parts game. If x equals u, then dx equals du. If dv equals e to the minus I n pi x dx, then v will be equal to 1 over minus I n pi x e to the minus I n pi x plus c, but we don't worry about the constant of integration for integration by parts in the first step. So that's the answer I have. So I can substitute that for my integration by parts. So u dv is uv minus v du. So keeping the half outside, u is just x, v is all of this, so x e to the minus I n pi x divided by negative I n pi, there's no x there, there's no x over here, it's just negative I n pi. And then this is from 0 to 1 minus v du. So when I integrate this, I'm going to get integral v is that. So actually that minus goes and cancels this. So I get 1 over I n pi. E to the dx is just du. So I'll write that dx there. Times e to the minus I n pi x. So we can evaluate the first part immediately, because at 0 it goes to 0, at 1 is the only contribution you have left. So the first integral is simple enough. It's e to the minus I n pi divided by minus I n pi. Now here I'll take the I n pi outside. The integral of e to the minus I n pi x is simply the same thing. 1 over minus I n pi e to the minus I n pi x. So I'll get another factor like that, e to the minus I n pi x from the limits from 0 to 1. Now observe a stroke of luck. I times minus I is precisely 1, because I squared is negative 1. So I'll write that here. Due to that, we simply get n squared pi squared in the denominator. Let me rewrite that. That's 1/2 negative 1 to the power n I over n pi plus, let's evaluate this at the upper limit. At the upper limit, I'm going to get e to the minus I n pi. At the lower limit, I'm going to get e to the minus 0, which is 1, divided by n squared pi squared. Well, let's now figure out what e to the minus I n pi, this is the answer, but it looks better if you can simplify it a little bit more so that people understand what it is that you have found. So let me use Euler's formula for that purpose. E to the minus I n pi is going to be cosine n pi plus I sine n pi. Now no matter what n is, sine of multiples of pi is always 0. Cosine, not so easy. If n is even, like 0, 2 pi, 3 pi, 4 pi, 6 pi, then cosine gets returned to cosine of 0, which is 1. If n is odd, like pi or 3 pi or 5 pi or 7 pi, then cosine gets returned to the other side, the negative axis. So there, the cosine value is minus 1. So you can encapsulate both results by writing it as minus 1 to the power n. If n is even, then minus 1 to the power n is just 1. If n is odd, then minus 1 to the power n is minus 1. You do a lot of these kinds of things in Fourier analysis. And that's one of the small minor challenges of Fourier analysis, to write things in a compact way to declare your answer, or to make the answer come out like it's supposed to be. So I'll write the answer as 1/2 -1 to the power n I over n pi plus -1 to the power n minus 1 over n squared pi squared. That is the coefficient Cn. Now, by the way, this also is valid for n equals 0, but for n equals 0, you have to take this limiting procedure of n tends to 0 of this type of thing, which is not that simple. So for n equals 0, my recommendation is to simply directly evaluate what it is. For n equals 0, this thing simply disappears, and I simply get that. So let's do the n equals 0 case separately, and that way we don't have to worry about these ugly limits. Integral 0 to 1 is just x dx. Well, that's just x squared over 2, is it not? So that's going to give me x squared over 4 because of the 2 that's present beforehand from 0 to 1, and that's just 1/4. Now, once you have C0 and all the Cn's written out, the entire series can be formally declared in the form of the Fourier series, and I won't write that. What I'm going to do now is show you how to get or recover the sine-cosine series from the complex Fourier series. That's actually a good exercise. So in some cases, it's always better to do the complex series first, because when you do things in the complex series, you can use essentially Euler's trick to solve the integrals, and then the real and imaginary cosine series can easily be found. So what we need to do now is to simply make a note that an is going to be 2 times the real part of Cn, and the reason for the 2 is because of the different normalizations. For C, you have 1 over 2 pi or 2L. For an and bn, you have 1 over pi or 1 over L. And that's the disconnect between an and Cn, because Cn, you see, comes from both sides. You have Cn's on the positive side and Cn's on the negative side. So An's are only on the right side. So you have to have 2 times Cn. Similarly, Bn is going to be -2 times the imaginary part of Cn. And A0 is going to be 2 times C0. So based off of that, you can simply get everything from that. For example, let's see what An is going to be. And for Bn, I'll refer you to the notes. So it's going to be 2 times the real part of all this up here. Well, that half I'll bring outside, so it'll cancel immediately. The real part of -1 to the power n times I, well, that is just going to be 0. Let me write the whole thing first. -1 to the power I over n pi. I'm going to do both the real and imaginary parts. It's not a big deal. -1 n squared pi squared. What you'll do is you'll ignore this part because that's got an I multiplying it. That does not have an I multiplying it, and so the real part is just this much. It's -1 to the power n minus 1 over n squared pi squared. And bn's are going to be the imaginary part. Again, you have the 2 by 2 cancellation, but notice the negative sign, so that negative sign should be respected there. -1 to the power n I over n pi plus real stuff, which is going to vanish when you take the imaginary part. So I end up getting just negative, but there's also a -1 to the power n inside over n pi. Now when you find the imaginary part of something, you don't write the I there. Okay, so that's -1 to the power n plus 1 over n pi, simplifying that result a little bit. And A0 is going to be 2 times C0, and C0 itself is 1/4, so A0 is going to be 1/2. So we can now finally write our series in terms of the sine-cosine series. Let's do that. F of x, remember it's A0 over 2, so that's 1 over 4, plus sum an cosine n pi x. So that's going to be A1 cosine pi x. Now what about n equals 2? Now when you put n equals 2, you notice that that's going to be 1 minus 1, because all even powers of negative 1 to the power n will just be 1. 1 minus 1 is 0. So only the odd powers will survive here. So I'll get a3 cosine 3 pi x and so on. That will be the story for the cosines. Sine, not so lucky. For the sine terms, all the n's will survive. So I'll just write b1 sine pi x plus b2 sine 2 pi x plus b3 sine 3 pi x and so on, where an's are got by the formula and bn's are got by this formula. So let's just spend half a minute more to write the final line. How would this be written with the an's and bn's put in? A1 is going to be negative 1 negative 1, so that's negative 2 over pi squared. Cosine pi x. For a3, I'm going to get the same negative 2, but because this is n equals 3, that's 3 squared or 9 pi squared. So that's going to be negative 2 over 9 pi squared cosine 3 pi x. And then it'll go even faster than that. For 5, it's going to be 25 pi squared cosine 5 pi x. Meanwhile, the b terms plus and so on, and the b terms are not going to gallop that quickly. In fact, they're going to be sedate. It's only going to go as 1 over pi. So that's going to be 1 over pi times sine pi x. For n equals, that's for n equals 1. For n equals 2, 2 plus 1 is 3, so I'll get a negative sign. 1 over 2 pi sine 2 pi x. And then it'll keep alternating between plus and minus. For n equals 3, I'm going to get 3 plus 1, which is 4. Negative 1 to the power 4 is plus 1. So plus 1 over 3 pi sine 3 pi x. And this is an infinite series, it never stops. So you can only write the first few terms. You can't write all the terms.